In this video, I would like to discuss NPSH and cavitation, and I will try to explain to you why ESPs are very rarely subject to cavitation. So let's start by explaining what is cavitation. So in a pump, when the pressure decreases below the vapor pressure of the pumped liquids, vapor bubbles are created. These vapor bubbles, they then move to the outer part of the vane and they collapse in a series of implosions. So these implosions, they create noise, vibration and a reduction of the head generated by the pump. So I have some good pictures over there that shows the effects of cavitation on a pump impeller. So you can see that the damage is quite severe. Now when we talk about cavitation, we also talk about the NPSH. So what does that stand for? It stands for net positive suction heads. And when we talk about NPSH, we refer either to the NPSHA or to the NPSHR. So the NPSHA is the available net positive suction heads. And what is the NPSHA? The NPSHA is a measure of how close fluids at a given point is to flashing, hence to cavitation. Flashing for a liquid means that its pressure has decreased below its vapor pressure, and hence you start to see some vapor bubbles being created. This is what we call flashing. So over there I have written the formula of the NPSHA. So this is a formula which is valid for the metric system. On another slide I will show you the formula in the imperial system. And so this formula is a simplified formula which is valid at the inlet of an impeller. So I let you read the formula and the corresponding elements that compose it. And now let's talk about the NPSHR. So what is the NPSHR? The NPSHR is the required NPSH, or the required net positive suction heads, and this represents the head value at the pump inlet which is required to keep the fluid away from cavitating. So the NPSHR is a value which is provided by the manufacturer. So your pump manufacturer will tell you if you want to avoid cavitation, you need to have an NPSHA which is going to be higher than this NPSHR. So the manufacturer will give you this value. On the other hand, the NPSHA is a system property. So it describes the states in which your fluid is at a given point. So when you use this formula, it is at the impeller inlet. So NPSHA describes the state in which your fluid is, while NPSHR is provided by your manufacturer. So to avoid cavitation, you need the available net positive suction heads to be higher than the required net positive suction head. So as mentioned in the beginning of that video, ESP are rarely subject to cavitation, and quite often when people say, oh, the pump has stopped due to cavitation, this is usually a mix-up with gas lock. So before I develop more on why ESP are rarely subject to cavitation, I recommend you two videos if you want to dig further on that topic. So starting from the second one over there, this one comes from a LinkedIn post and you will see a pump that gets subject to cavitation. So it's quite interesting to see the behavior of that pump, so how it starts to vibrate. And the first one is basically a training video that explains what is cavitation and explains the NPSH into more details than what I just did. On this slide, I wanted to show you an example of NPSHR, so required net positive suction heads data provided by a pump manufacturer. So this one is a curve for this ESP pump, which is provided by Oil Dynamics, which is a German company. And what we can see is that the NPSHR is not a fixed value, it's a curve that we can see in reds, and we can see that it increases with the flow rate. Typical value for the NPSH of an ESP, it usually ranges between 2 to 10 meters, so basically 5 to 30 feet. And we can see that for this particular pump, it ranges between 4.5 to 7.5 meters. So what is that in feet? 13 to 22 feet. So why are ESPs rarely subject to cavitation? To understand that, we're gonna take a look at any of these two formula and we're gonna try to do a bit of calculation. So over there, I just copied again the NPSH formula using the metric system, and just down there, this is that same NPSHA formula, but using the imperial system. As mentioned on the previous slide, the required NPSH of an ESP typically ranges between 5 to 30 feet. Now, when you operate an ESP, you will operate it with a minimum pump intake pressure, and this minimum pump intake pressure is rarely below 100 psi, and it is usually above 150 psi. So why do we do that? We basically want to operate ESP pumps with some liquid submergence above the pump intake to avoid running the pump dry, which could really damage it. So ESP pumps are usually run so that if the pump intake pressure were to drop below a certain value, somewhere between 100 to 150 psi, the pump would stop to make sure that it will not run dry. So then, going back to the NPSHA, ESP are usually operated with a pump intake pressure above 100 psi. Now, what happens if we try to calculate the NPSHA of our ESP in that configuration? This absolute pressure at the inlet, in the worst case, it will be 100 psi. Now, to be conservative, I'm gonna assume that I am producing only water, meaning that the specific gravity of the produced fluid is going to be maximum, so it's going to be equal to 1. Had I chosen oil, it would have been around 0.8, meaning that this term would have been bigger. So there I am being conservative and I take 1 for water. I'm also going to be very conservative and I'm going to assume that there is no fluid velocity at all. So if I assume that, then this term is equal to 0. It is very conservative because when you produce from your reservoir, the fluid is moving from the perforation into the pump. Hence, you do have fluid velocity at the pump inlet. So by choosing 0, I am being very conservative. Now, what I need to remove is this term over there, and over there I have the vapor pressure of the pumped fluids. Now, the vapor pressure of oil is typically much lower than that of water. So if I want to be conservative, I will consider that I am pumping water, and so this vapor pressure is going to have the maximum value. So the vapor pressure of water is 0.49 psia at 77 degrees Fahrenheit and 0.92 psia at 140 degrees Fahrenheit. So when you are at 1000 meters or 3000 feet of depth, 140 degrees Fahrenheit is a quite common temperature. So we're going to take this value for the vapor pressure of the water. So here I'm going to use 0.92. So now if I calculate this term over there using the different values that I've written around there, I will find a number that is smaller than the NPSHA. So let's take a look at this. So I will have 100 psia divided by 0.433 plus 0 because I assume 0 velocity, and minus 0.92 divided by 0.433. So as you can see, then it becomes 100 minus 0.92 divided by 0.443. So this is more or less equal to 99 divided by 0.433. And so this gives me about 228 feet. So by being very conservative this way, considering that I am operating my ESP with a very low pump intake pressure of 100 absolute psi, I know that my available net positive suction head is going to be higher than 228 feet. And as mentioned over there, the required NPSH of an ESP typically ranges between 5 to 30 feet. So over there I have 228, meaning that if I consider a required NPSH of 20 feet, the available net positive suction heads at the inlets of my ESP is about 10 times higher than the required NPSH. And so that explains why ESPs are very rarely subject to cavitation, because you typically have a very big margin between the available net positive suction heads and the required net positive suction heads. So on a field, when you hear that, oh, the pump has stopped due to cavitation, keep in mind that it's probably not the case, and what most probably happens is that you probably went to gas lock, too much gas went into the pump, and so the pump stopped generating heads, lost its ability to pump the liquid from your well, and so it tripped for that reason.